All right, good morning everyone. Welcome back to our weekly physics live stream. Today we're going to be talking about Gauss's law. So we're going to continue what we have started last time, which is last time was the first chapter of Physics 2, electric fields. And we had mentioned that, okay, well, we need to somewhat get an understanding of what electric fields are and how they relate to the electric force, in particular between 2-point charges, but not exclusively. And we ended on the slice and dice method, saying that, well, not everything in the world is a point charge, and so we need to be in a position where we can find the electric field, perhaps of a semicircle of charge, or a ring of charge, or maybe a rod that has a finite length and a certain amount of charge on it. And so because we started going towards things that are not point charges, that are called charge distributions, right? That's charge distribution is just an object that has charge, and it can have charge over its length, throughout its surface, or throughout its volume. And we said, okay, slice and dice always works, but the price to pay is that you have to do an integral. You have to integrate over the charge distribution to get your electric field. So that's the price to pay. Sometimes it's a hefty price. Sometimes it's too hefty to do by hand, and so that's a bit of a bummer. But there's a few cases that you can do by hand. Now, there's also the case of objects that have sufficient symmetry that no calculus is required at all. That's not exactly true. It's that whatever little calculus is required, it ends up breaking down to something that is not calculus at all, really, and is just multiplying the magnitude of the electric field by the right area and setting that equal to Q enclosed over epsilon naught, which is, in other words, Gauss's law. So Gauss's law is the continuation of what we were doing. We had, okay, slice and dice works all the time, and then in certain cases, we could do slice and dice, but our life will be infinitely easier if we apply Gauss's law. So the goal of today is to discuss Gauss's law and to kind of first wrap our heads around what we're doing on the technical side and how, because of the symmetry of the charge distributions to which we can apply Gauss's law, we do get our hands on the electric field in the end, because it doesn't look like it. It looks like we're going to focus on flux, but it turns out flux is really a means to an end. It's a way to get the electric field. So we need to talk about that, and we need to basically try to get as familiar as we can with Gauss's law. The joke is that, to apply Gauss's law, you have to believe in Gauss's law, because it's a little strange at first, and particularly the fact that we only focus on the enclosed charge. So, but that's even getting ahead of ourselves for now. So we are going to, today, talk about Gauss's law. In order to do that, we're going to first define electric flux, because separate from Gauss's law, you can define electric flux. We're going to try to wrap our heads around what that is, and then in the context of Gauss's law, we're going to try to understand why knowing what the electric flux is and setting it equal to Q enclosed over epsilon naught allows us to derive the magnitude of the electric field. And of course, there are restrictions. You can't do it for just any old object if your goal is to get the electric field. But for certain objects with a lot of symmetry, it's going to work. So we'll do the example of the point charge. That's just to illustrate how you apply Gauss's law. It's very simple, and we already know the answer, but it's kind of just to get, an idea of how you go about applying Gauss's law and what the philosophy of it is. And then we'll do some classic charge distribution. So we'll do the cylinder of charge, either charge on its surface or throughout its volume. And we'll also do nested charged objects, which is also a classic. So there's a lot of stuff we need to talk about, and it's an important chapter because it's the missing half to the first chapter. The first chapter emphasizes a little bit more defining electric fields and how they relate to the electric force, how we draw field lines and things like that. But then at the end we start doing slice and dice, and then Gauss's law is the complement that says, okay, now we have slice and dice and Gauss's law, so that for many different objects that you can provide me with that carry charge, I can find the electric field. Maybe not everywhere, maybe just at a certain point, but still, I have a lot of tools at this point to take a charge distribution and find the electric field. All right, so let's just get into it, because talking about it is nice, but it's not as nice as drawing stuff out and writing stuff out. So this is chapter 2, Gauss's law. As usual, here are all the resources. If you want to get all these live streams, the practice problems, and solved homework problems, you can go to slackademia.com/live streams, and you can sign up for the Physics 8B live stream. It's free, and you get access to all the content. It's nice and packaged and organized. There's even the old live streams from previous years while we run through the new ones. So I'm updating them right now, but the old ones are still there if you want to get ahead. So it's a nice resource and it's free. You should go check it out. And of course, if you want a study guide to help you study, you can get one, or we can make one for you, and then you can sign up. And if you want even more help, if you want me to help you with physics this semester or this quarter, you can sign up for Masterclass. And the Masterclass comes with a guarantee that if you don't get some kind of A, you get 90% of your money back. That is hopefully a no-brainer. If you find a cheaper tutor, you should hire him or her. All right, so Gauss's law. Now, Gauss's law is going to look strange at first, but bear with me, you're going to love it in the end, okay? Because it is really, really nice to be able to use Gauss's law to find the electric field. It's a lot faster and cleaner than having to do slice and dice. So let's start with the definition of electric flux. Okay, because that is a strange quantity, and we kind of have to get our mind wrapped around this before we even talk about Gauss's law. All right, so electric flux, the idea is that I would like to count field lines, which, you know, doesn't seem that bad. I mean, if you think of it, we said, okay, you know, Q, positive point charge, is going to create electric field lines, in fact, in all directions of space, kind of like a disco ball with light. Okay, it's going to create electric field lines that radiate away from it in all directions of space. So, well, you know, maybe I can count them, right? So if you gave me a disco ball, maybe it has, I don't know, 200 little mirrors on it, and I could count and be like, oh, there's 200 beams of light, okay? Well, but that's a disco ball, and that's nice, but point charges, I mean, point charge doesn't work that way, because electric field lines, we decide to draw a few, and I drew 4, but there's no reason why I should stop, because the electric field permeates all of the space surrounding the point charge continuously, and so I could draw more. I could draw 8, but if I really wanted to draw 16 because I had a little bit of more time, I could. And so there is no rule that says I have to stop drawing field lines. I can draw as many as I want. So then the question is, well, how the heck am I going to count them? Because if it's up to me to decide how many I draw, it doesn't seem very reliable to try to count them by hand, which is a valid point. So it's not straightforward how you would go about counting electric field lines. It also isn't straightforward why you would care. Don't we have better things to do? But the truth is, we said, okay, number of field lines is proportional to charge, right? So if we have 2 point charges and one is double the other, well, the one with double the charge would have double the field lines. So in a sense, it measures the strength of the electric field in a way. So let's just assume that we are interested in counting the number of field lines. We just have to find a way to do it. All right. Now, the way we're going to do it is we're going to count field lines that go through a surface, right? You can think of it, it's not a perfect analogy, but you can think of it as, it's kind of if you were shining a bunch of laser beams through a window and you were going to count how many laser beams go through that window, right? You buy a bunch of lasers, shine them all through the window, and you want to figure out how many go through. Sort of. It's kind of the idea. And we're going to use that surface because it makes sense that, well, if you have a very big window, you'd have to buy a lot of lasers. You'd have a lot of laser beams. If you have a small window, you'd have less. So somehow the surface area kind of factors in the fact that, well, the bigger the area, the more flux, the more field lines through that surface. And so let's consider the following. Now, to be clear, this is a perspective view. Yes, this is a horizontal surface, but coming out of the page in perspective, right? So we have this surface coming out like this, and this surface has an area A. And let's assume that we have an electric field permeating the entire space. And this is an electric field that is slanted like this a little bit, okay? And of course it exists. Let me do this. There we go. It exists everywhere, and it pokes through the surface here, like that. Okay? And we're going to try to figure out how much of it goes through the surface. Because if you think about it, your electric field has two components. It has a component here that is E, we'll call it E parallel because it's parallel to the surface, right? Now that's the horizontal component, if you want to call it that. The point is that relative to the surface is just the component that is parallel to the surface, okay? But it also has another component, right? It has a vertical component like that that is in fact perpendicular to the surface, right? So here we have E perpendicular. All right. Now, typically what we would do is we'd introduce an angle. We could introduce this angle theta or this one, and it doesn't matter which one you choose to label theta. As long as you choose one, you can find the components. Now, that's in general. When it comes to flux, the rule is that we choose the angle relative to what's called the normal. Well, the normal just means perpendicular in math, and so the angle will be measured between the electric field and the direction perpendicular to the surface, which is going to be the vertical. So we're going to choose this angle to be theta. Okay? And we want to figure out how much of the electric field goes through the surface. Now, perhaps a quick reminder. The dot product between two vectors. All right, let's say we have two vectors, A and B. This is B, and this is A. And that there's an angle between them, let's just call it theta. And there will always be an angle theta between the two. If you take two chopsticks, right, and you put their ends together, right, like maybe in the palm of your hand, and you try to hold them however you want, there will always be an angle. You could make it 0. You could put them in the same direction. You can make it 180 if they're opposite directions, or you can make it anything you like. But two chopsticks will define a plane, and there will forever be an angle between the two. It could be anything, right? And so A dot B, the dot product between these two vectors, is going to be magnitude of vector A, which is A, magnitude of vector B, which is B, cosine theta. And this measures how much of A is along B. Turns out it also measures how much of B is along A, because you can, A dot B is the same thing as B dot A. But the point is, what the dot product does is that it tells you how much of a vector is along another, right? And if we come back to flux and we say, well, we would like to figure out how much of this electric field goes through the surface. Well, the best way to go through the surface is to point in this direction, along E perpendicular. Then you go straight through. Because if you're along E parallel, you do not go through the surface. You're parallel to the surface. So you're grazing the surface, right? But you're forever contained within that surface. You never poke up or down, so you don't cross it, right? So E parallel is a component we don't care about. In fact, the only component we do care about is E perpendicular. That will be the fraction of the electric field that actually goes through this surface, okay? So I would like to figure out how much of E is along this direction, and therefore I need to give this direction a name. Now this direction is the perpendicular direction. Again, in math we call it the normal direction, and we're going to introduce what we call the normal vector. Now the normal vector is an extremely clever quantity, okay, and we'll see why. First of all, the normal vector, I'm just going to draw it. It's going to be perpendicular to the surface. We're going to call it vector dA. Okay, now there's a good reason for that name, so bear with me. And the vector dA is going to have two properties because it's a vector. It has a direction, which is the right direction. It's perpendicular to the surface. It's the direction I'm interested in. And it's going to have a magnitude. And I'm going to be extremely clever with the magnitude. I'm going to say, well, you know, I'm going to give it a magnitude that's going to be called dA. But what dA is going to represent is this tiny piece of area here. Right? That tiny piece of area, we're going to say is, well, it's the smallest area you can imagine that's non-zero. But that play tricks on your mind, maybe. So let's simplify it. And mathematicians, I know it's not that rigorous, but I don't care. Let's say that dA is the area through which I can only fit one field line. Let's just call it that. Okay. And so then I have this electric field that is going through the surface, and the tiny amount of flux that's created by just this one field line, we're going to call d phi e. Now, phi e is the electric flux, but d phi e is the electric flux from one field line. Okay? That's just going to be E, the electric field, dot dA. Okay, now by definition of the dot product, E dot dA measures how much of E is along the vector dA. But the beauty of the vector dA is that not only does it have the right direction with the angle theta between E and dA, but it also has the right magnitude. So it's going to be E dA cosine theta. Right? That's just this, it's just the application of this formula. Now, we don't usually use it or write it this way. We tend to write it E cosine theta dA. It doesn't really matter, yeah. But we like putting dA at the end because once we integrate, it makes a lot more sense. Okay, so this is flux going through the small area dA. In other words, it's the flux created by one field line. Then the question is, well, you said that we have this electric field everywhere. So presumably, we have field lines like this absolutely everywhere. And nice, we have the flux from one of them. How do I account for all of them? Okay, well, I could try to count them by hand. But that's not going to work because I don't really have a finite number. I have a continuous distribution of electric field lines that are going through this surface. So I need to basically create this infinite sum over a continuous quantity, and so that's really an integral. And so this is going to be the electric flux created by one field line. All right, this has a name. It's called the infinitesimal electric flux. Okay. Don't worry, it's just mathematicians like to use words that you do not understand, but that's all, right? That's the only point of that. But the name is infinitesimal electric flux. It is the smallest electric flux that you can imagine that's non-zero. In other words, let's call it the electric flux from one field line. And the electric flux through the entire surface, so electric flux through the surface A that we drew above is going to be phi sub E is going to be the integral of E dot dA, which is going to be the integral of E cosine of theta dA. Okay. Now, there's a notation thing going on here. I wrote a single integral sign. If you do that, you typically put a subscript A to indicate that it's the integral over the area. Right? Sometimes you'll see people write the double integral of E dot dA. And okay, if one single integral is over dx, over one direction of space, one variable. Two integrals just means the same thing. It's the integral this time over two variables, so over an area. Okay, so it's equivalent notation. I usually tend to like the double integral sign instead of just one with the subscript A. It's really just force of habit. I spent way too long doing physics with double integrals to give them up. But it means the same thing. Okay, so you could write it however way you want. it's not going to matter because the whole beauty of Gauss's law is that even though this is calculus, we're not going to end up doing calculus, and we'll see why. So this is our electric flux through surface A. This is going to count how many field lines go through this surface. And it's an electric flux. It is therefore going to be measured in Newton meter squared per coulomb. Newton per coulomb is for E, meter squared is for the surface area. So those are the units of flux. Okay? So it's a bit of a weird quantity, but if you accept that perhaps we'd like to know how many field lines go through a surface, that is how you would compute the electric flux. That would tell you how many field lines go through that surface A. Okay, so with that said, let's tie it to Gauss's law. Now, Gauss's law is going to say the following. It says that the electric flux through a closed surface is proportional to the charge enclosed by the surface. All right. Now we're gonna see how that hopefully makes sense, especially when we do the example of the point charge. Okay, but let's go back to my disco ball. Let's say I have a disco ball that has 200 little mirrors on it, right? If I shine light on it, let's say for simplicity, I get 200 beams of light because there's 200 mirrors. Okay. What if I have 400 mirrors instead? I double the number of mirrors. Well, then I should get, again, simplifying, 400 beams of light. I should get twice as many beams of light, okay? So the same idea with charge. If I double charge, I should have twice as many field lines. So it kind of makes sense that if doubling charge will double the number of field lines, well, then the flux ought to double as well, because now all of a sudden for a given area, I would have twice as many field lines going through. And the factor of 2 is directly proportional to the charge that I have to begin with. So that's the idea, the simple idea behind Gauss's law. Okay, now let's see how we carry it out, because we need to be a little bit clever as to how we choose this closed surface in question. Okay, but one way to write this is the following, is to write that the flux, let me write this with the same color red here, the flux through some surface A, so the integral over the area of E dot dA, is going to be equal to, the Q enclosed is going to be the charge enclosed by the surface, and divided by epsilon naught. 1 over epsilon naught is the proportionality factor, okay? And, well, because we said that the surface has to be closed, which makes sense because if it's not, it cannot enclose charge, right? Well, we have to somehow indicate that in our notation, because if I just write this and I don't remember that the surface is closed, I might just think that this is this, and after all, I applied it to a surface here that's not closed. It was just a rectangular surface, right? So we have to be a little bit careful with our notation. What we do is we put a ring around the integral, and the ring around the integral means that the surface is closed. That's just notation, okay? Now, the goal is to find E not the flux. Now, it turns out I need to know what the flux is to find E, but finding flux with Gauss's law is quite straightforward. I would just have to account for the amount of charge enclosed and divide it by epsilon naught. And then I could report back and say, hey, my electric flux is, I don't know, 100 Newton meters squared per coulomb. You're like, okay, thanks, John, but we don't care. It's like, well, why? Well, because I actually don't care what the number is for the electric flux. I care that the electric flux involves the electric field. And I hope that it breaks down in such a way that I can pull the electric field out from this equation and solve for it. That's what I want. So whether flux is 100 or 75 or 200, that's not really helpful to me, not directly anyway. So how are we going to do that? All right, so that's the goal. The art of Gauss's law is choosing the right Gaussian surface. Okay, that's going to be the art. Now, spoiler alert, cylinders, okay, not just hollow cylinders, like hollow cylinders with end caps, a top and a bottom, so like a can of beans, you know, or spheres are going to get the job done every time for everything we need to worry about in this class. So we're not going to go imagine weird Gaussian surfaces. Cylinders and spheres get the job done. Okay, so in this class, cylinders or spheres. Okay, now how we choose whether to use a cylinder or a sphere, we're going to get to that. Okay, and within choosing the right Gaussian surface, it must be such that E is constant in magnitude and direction over the surface. Okay, because if it is, math tells me that I get to do the following. Okay, I get to say that my flux through my closed surface, so the integral through the closed surface or over the closed surface of E dot dA is going to be the integral over the closed surface of E cosine of theta dA. But if E is constant in magnitude and in direction, that means that E and theta are constant over the entire surface. Well then, integrals don't care about constants. It doesn't matter if they're integrals over area or they're over closed surfaces, they still don't care about constants. So I can pull this thing out, right? I can just take E cosine theta and pull it out, and I get E cosine of theta, the integral of dA over this closed surface. Well, you can think of dA as the tiny piece of area. That's what we said, right? In fact, it's the smallest area you can imagine, the area through which I can only fit one field line. If I account for all the possible dAs over my surface, in other words, if I integrate just dA over my entire surface, I get the surface area. You can think of it as a mosaic, right? If you added up all the little tiles, you get the full surface area. It's not quite the right analogy, but it's the same idea. The point is, this simplifies to E cosine theta times A. Okay. Why do I want that? Well then, the consequence of this is that by Gauss's law, we have electric flux through a closed surface is equal to Q enclosed over epsilon naught. Okay, but now you're telling me that flux is E cosine theta times the area is equal to Q enclosed over epsilon naught. Okay, so that's what I was saying. I don't actually care what the flux this whole thing is equal to. I care that I can get my hands on E, and then I can solve for E. Right? I just isolate E and I get the magnitude of the electric field created by this distribution. Okay, so this sounds very abstract, and it is right now. So just bear with me. We're going to do an example that hopefully kind of clarifies things, but it's kind of important to have this foundation. You have to understand that Gauss's law, the goal is to get the electric field. We do not care what the flux is. We care that we choose a Gaussian surface in such a clever way that we get to go from here to here, because what we want in the end is to get our hands on the electric field. Okay, and if it's hiding inside the integral, I can't get my hands on it. I want it to pop out and then have e cosine theta times the area. Hopefully the area is easy to compute just with geometry, and then I can solve for E. Okay, so let's do an example. And then we'll do some practice problems. But this example, it's going to be a very simple example. We already know the answer anyway because we're going to apply it to the point charge, but it's going to be important to see how you would go about choosing your Gaussian surface and then applying Gauss's law to get the electric field. Okay, so we have here a point charge Q, positive, let's say. Okay, plus Q just to be clear. And we know that Q creates field lines that radiate away from it in every direction of space. So I'm going to try to do my best to represent that, right? I'm going to say, okay, well, let's just do this. Okay, this is going to be a sphere, and then I'll draw one of the field lines, right? I'll draw this one. But there are many like this one. They all go from the center radially outward, right? Like that. Okay? And that's true everywhere around Q. Like, there's no reason why what happens here should be any different than here, here, or here, right? It has perfect spherical symmetry, is what it's called. Okay. And so maybe we even do the following. Maybe we draw a 2D representation of this, because you'll see that more often than not we don't draw things in 3D. It's just too much work. We just draw it in 2D and we know whether we're dealing with cylinders or spheres, and we go from there. Okay, but let's just humor this. Okay, we would like to figure out the electric flux through a closed surface, and we would like to choose a surface over which the electric field is constant in magnitude and direction. Okay, well, if you have spherical symmetry, all the points on the surface of this sphere are the same distance from Q. So everywhere you look, the electric field is going to have the same magnitude on the surface of the sphere by symmetry. And in fact, an interesting property is going to be that it's also going to be perpendicular to the surface of the sphere everywhere. So this sphere is actually a good choice, turns out. It's a good choice because everywhere on the surface of the sphere, E is constant in magnitude, but also in direction. So, this is going to be harder, so let's just do this. Let's consider this sphere, right? Let's give it a radius r. We'll call it little r on purpose. That's also a very clever choice. And we're going to say that, well, if we look at our sphere, I'll draw it in 2D here, right? This is just a 2D representation of the same thing. We have an electric field that is perpendicular to the surface and constant in magnitude on the surface. And so now if we choose our normal, dA, it's going to look like this. It has to be perpendicular to the surface, right? And it turns out it also has to be outward. So that's actually a convention from math. Math tells us that when you have a closed surface, the proper orientation of the normal is outward, which is fine because outward flux is going to be positive, and that's because if you have positive enclosed charge, E radiates out. If you have negative enclosed charge, E radiates in, and inward flux is going to be negative. Okay, so dA always has to be outward relative to the surface if it's a closed surface. But okay, fair enough, right? E is going to be along dA everywhere. So we have two things that are true. E is constant in magnitude on the surface of the sphere,
And then theta is equal to 0. No, not Celsius, just 0 degrees. So theta is equal to 0 degrees between E and dA everywhere. Right? It doesn't matter where you place yourself on the sphere.
E and dA will have an angle of 0 in between them. They point in the same direction, which is outward. Okay? Now, to address the elephant in the room, it's like, no, but okay, hold on. What is this sphere? Why is there a sphere? Does it exist? Does it not exist? And that's a fair question. So it's the most confusing part about Gauss's law. The sphere that I drew is a mathematical abstraction. Yes, it is a sphere that I place onto the problem because it is the right choice given the symmetry of the electric field, to then evaluate flux through the sphere and eventually get the magnitude of the electric field. So it is a disposable sphere, if you will, that I place on the problem to do a calculation, and then I don't need it anymore. But it does not exist. It is not a physical object, and it is just a mathematical instrument that I use, and then I don't need it anymore. Okay? But I do need it to compute flux, right? So let's compute the flux over the closed sphere of our electric field. So that's the integral over the closed surface of E dot dA. That's going to be the integral over the closed surface of E cosine of theta, which is 0, dA. Okay. E and cosine theta are constant on the surface of the sphere by symmetry. So I get E cosine theta, but theta is just 0, right? So it's E cosine of 0, which by the way is equal to 1, so that's nice, times the integral over the closed sphere of dA. Okay, and again, dA is the little piece of area here through which we fit one single field line. Okay, well, if I integrate all the dAs around the whole sphere, all the mirrors over my disco ball, I get the entire surface area of the sphere. And the surface area of a sphere of radius little r, if you don't already know it, you should remember it, is E and then times the area of 4 pi r squared. So the surface area of a sphere of radius little r is 4 pi r squared. Okay? So I've managed to choose a surface that simplifies flux to E times area. And even better, cosine theta is 1, so that's nice. Okay, I need to equate that to Q enclosed over epsilon naught. All right, well, how much charge do I enclose in my Gaussian sphere? Well, within all of this volume, there's only Q. So my enclosed charge, in this case, is quite straightforward. Sometimes a little trickier, but here it's easy. It's just Q divided by epsilon naught. Yeah? Okay. So then, by Gauss's law, it has to be the case that E, 4 pi r squared, is equal to Q over epsilon naught, which means that E is Q over 4 pi epsilon naught r squared. I already knew that, right? The same thing as KQ over r squared, and we've known that since last week. But there you go. All right? Gauss's law gave me the electric field. And yes, I already knew the formula, but still I land on my feet. And how did I do it? Well, I applied Gauss's law, and all I had to do is be clever about choosing the right surface. And again, we're choosing between spheres and cylinders in this class, so you don't have a million options to choose from. What dictates whether you use one versus the other is the symmetry of the electric field. Okay, here it has spherical symmetry, right? It has no preferred direction. So by definition, spheres have no preferred direction, and therefore we will use a sphere as our Gaussian surface. But sometimes we will use cylinders. So in fact, we're going to do a problem right now where we're going to use a cylinder, which is important because we need to see both closed surfaces in action, if you will, so that we understand how to evaluate flux through a sphere and through a cylinder. It's a little bit more technical. Through a cylinder, you have to be a little bit more careful, but those are our two options. And once we do enough examples, of each, then we should be pretty good at evaluating flux through a closed surface and applying Gauss's law. And at that point, things become a lot more fun because it becomes a lot easier to find the electric field by applying Gauss's law, assuming that we have the symmetry. All right, so with all of that, let's come down here and have a look at this cylinder of charge problem. Okay, so this is an extremely classic type of problem. And I considered two different cases because I wanted to make sure that we covered both, because the answers are a little different and we get to then see both sigma and rho, which are the surface charge density and the volume charge density. Okay. So we have an infinitely long cylinder of radius r, okay, which of course is an idealization. Such a thing does not exist. You cannot buy an infinitely long cylinder on Amazon, but it is an idealization. And by the way, let's talk about this, because we say, oh, you need enough symmetry to apply Gauss's law. Well, what do you need? You need an infinite line, like a fishing line, or cylinder. They have the same symmetry, cylindrical symmetry. So you have an infinite line of charge or an infinite cylinder of charge, then you have sufficient symmetry. If you have an infinite sheet, also an idealization, then you have sufficient symmetry. And then if you have anything that's spherical, typically you have the symmetry. Of course, an infinite sphere does not exist. That doesn't make any sense. Right? A sphere is going to be finite in size and volume, but as long as you have something spherical, typically you'll have spherical symmetry. You could make that not true, but you're really being mean at that point. So let's just remember that those are the three geometries or symmetries that work: infinite line or cylinder, infinite sheet, and anything spherical. Okay, and you might say, well, okay, well, obviously nothing is infinite. I can't buy an infinite cylinder of charge, and I would say that's true, but maybe you can buy one that's long enough. Let's say you go buy a cylinder that's, I don't know, 3 feet long. Okay, 3 feet. Okay, 3 feet is not infinitely long. I get it. All right, and let's say that this is 3 feet. But then you're going to tell me, well, really all I care about in what I'm trying to build is the electric field right here at 0.001 inches from the surface, right? And it's going to maybe point away like this if it's a positive cylinder. But I want to find the electric field really close to the surface. Okay, well, if that's the case, this relative to 3 feet means that it's a reasonable assumption to consider the cylinder as infinite. Okay, as long as you're somewhat in the middle here, looking for that electric field. But if that distance, 0.01 inches, is very small compared to the length of the cylinder, it's not a bad approximation at all. Okay, so that's kind of how we use it in practice. Obviously, in reality, we will have things that are not infinite, but if they're long enough compared to how close we want to find the electric field, let's say, then we'll say, okay, let's treat it as an infinite cylinder because it makes it easier. Okay, because if it's not infinite, then at the ends here, the electric field stops to be nice and symmetric. Right, so let's draw this, the electric field for this thing. Let's say we have sigma. Sigma is positive. Now, what is sigma? Sigma is charge per area. So we took this cylinder and we kind of spray painted charge on the outer surface. Okay, so there's a certain amount of charge per area. That's sigma. That's what sigma represents. And let's say that it's positive. Okay. Well, if I place myself in the middle here, the electric field is going to radiate away from the center like this. Okay, but this is perspective, just so that we're clear, yeah, that this is going to be, all right, and it's going to do the same thing on the other side. It's going to, okay, so E is going to be radially outward. In a horizontal plane, E is going to point away from the center in all directions, okay, but it's horizontal. And if in fact the cylinder is infinitely long, well then E will remain horizontal everywhere. Everywhere you look, you'll have E radiating away in a horizontal plane. If instead you have a finite cylinder,
Well, then when you get towards the edges, you have what's called fringing, and it gets all messed up, and E starts to goof around and starts to do stuff like this, and then like this, and then you're like, ah, god damn it. This kills all my symmetry. My nice symmetry here, where E was always radially outward, goes away at the edges of a finite cylinder. So if I could get a finite cylinder, that would be the best. Since I can't really get one in real life, maybe I can kind of treat it as if it were infinite and simplify my math. Okay, so that's kind of a sidebar right there, but that's why we simplify things and consider infinite lines of charge, infinite cylinders of charge, and infinite sheets of charge, because it maintains the nice symmetry. Okay, so that's what the electric field looks like, yeah? And we assume that we have a conductor with a surface charge density sigma, all right? Find the electric field as a function of a distance r from the axis of the cylinder. Okay. So this cylinder has two regions. I'm going to call region 1 and region 2 the two regions. Region 1 is inside the cylinder, and region 2 is outside. And this is a solid cylinder, right? It's not hollow. It's like a rod of metal if it's a conductor, okay? All right, so in each region, we need to find the electric field, and we should not assume that we have the same electric field in each region. That's probably not the case. Okay, so we're going to start with the inner region and move outward. You could go the other way. It's just force of habit. I like to go from the inside toward the outside. I think it makes a lot more sense most of the time. So let's look at region 1. Okay, region 1 is for little r less than big R. We'll get to that. It'll make more sense in a second. But what did we say? We said that our electric field looks something like this. Yeah, it's going to be radially outward. I'm going to call it E1 for region 1. But that's radially outward in all directions within a horizontal plane, right? So E is going to look like this. Okay, and in fact, everywhere I look, E is going to look like that, right? Because I'm assuming my cylinder extends infinitely. So maybe I draw another set of electric field lines up here. Right, I draw this. And then I draw this. Okay, and so that's going to be my electric field. And, well, bear with me. I'm just going to, I won't draw all of it here, I'll draw these two just to have them. Okay. So everywhere I look, if I walk around this cylinder, I always find E, leaving it horizontally and going radially outward because it's a positively charged cylinder. Okay. And I know that this is the right symmetry to apply Gauss's law, so let's apply Gauss's law. Now this is not spherical symmetry. There is a preferred direction when it comes to my cylinder. That's the vertical direction. Horizontally, there's no preferred direction, right? It's like this is equivalent to this is equivalent to this. In the horizontal plane, all the electric field lines leave the cylinder. But the vertical direction behaves differently, right? So there is a preferred direction for a cylinder. So I wouldn't want to use a Gaussian sphere. Instead, I'm going to use, well, a Gaussian cylinder, since I'm allowed to do that. Okay, and so I'm going to draw a Gaussian cylinder. And the thing is that my Gaussian cylinder, if I want to find the electric field in region 1, my Gaussian cylinder is going to have to live in region 1. So let's zoom in here so we see what we're doing. Okay, so I'm going to have to make it fit within my cylinder here. So I'm going to draw a Gaussian cylinder. Like this. I'm going to give it a radius little r. That's why we said little r is less than big R, okay? So that the cylinder lives within region 1. And I'm going to compute the electric flux through my Gaussian cylinder. And the reason I need it to be within region 1 is that when you compute electric flux with Gauss's law, the E that you get is E on the surface of your Gaussian surface, if that makes sense. Or so it's E on your Gaussian surface, if you want to say it that way. So if you want E1 within the cylinder, well, your Gaussian surface needs to live within region 1. Okay. Now my Gaussian surface here is a cylinder, it's not a sphere. Sphere is pretty easy. You know, we said the normal dA is always outward, and for that matter, well, in the case of a sphere, it's pretty easy. There really is only one surface. But for a closed cylinder, there are 3. There's the top, the bottom, and the cylindrical wall. Right? It's the toilet paper roll, and then you put a top and a bottom on it. You put end caps, and that's your cylinder. So you have 3 surfaces to deal with, right? Now for the top, well, let's introduce dA1. dA1 is going to be vertical because it has to be outward, relative, and perpendicular to the top, so that's the only option. Same logic is going to get us dA3 down here, pointing down. And then for the cylindrical wall, well, dA2 is going to have to point out and be perpendicular to the cylinder wall. And so it's going to look like this. And by the way, everywhere I look, as I go around, dA2 will always be along a field line, right? Because the field lines are going to be radially outward in the horizontal plane. So it's a little bit more work to set up a cylinder if you're applying Gauss's law and to compute the flux through it, but it's always the same process. So once you get used to it, it's not that bad. Okay, so I want to evaluate flux on the one hand, and then I'm going to equate it to Q enclosed over epsilon naught. Okay? So let's start with flux. The flux over the closed cylinder, so the integral of E dot dA over the closed cylinder is going to be equal to, well, I need to break this up into 3 integrals, the top, the bottom, and the cylindrical wall. Each one of those is not a closed surface, right? The top cap here is not a closed surface, the bottom one isn't either, and the cylinder wall is not either, right? So I'm going to write the integral without a ring around it of over A1 of E dot dA1 plus the integral over A2 of E dot dA2 plus the integral over A3 of E dot dA3. And to be really consistent, I should call this E1. All right. Now, let's start with the first integral. A1 is the top surface. Okay, this is going to be E1 times cosine of the angle between E1 and dA1. Well, E1 is horizontal, dA1 is vertical, therefore the angle is 90. Cosine 90 is 0. What does that mean? It means no flux through the top surface. Well, actually that makes sense. If E is horizontal, it can never poke up through that surface or down through that surface. It's horizontal. It just grazes the surface. So this is your E parallel, if you will. All of E1 is parallel to the surface A1. No flux to the top. For that matter, I expect no flux to the bottom either. I only expect flux through the cylindrical wall. So here I'm going to get the integral over A2 of E1 cosine of the angle between E1 and dA2 times dA2. Well, what's the angle between E1 and dA2? Well, have a look here. Hopefully you're convinced that the angle is 0. They both point in the same direction, which is outward, right? So the angle between the two is 0. All right, now cosine 0 is not 0, it's 1. Okay, so that's actually nice. Not going to cancel the integral. And then for A3, well, it's the same thing as A1. So I'm going to get E1 cosine of 90 dA3.
That's going to be 0. So no flux through the top or bottom, only flux through the cylinder wall. On the cylinder wall, as I walk around like this, I will always see an electric field that's perpendicular to the surface, and since all the points of that surface are the same distance, little r, from the center, by symmetry, there's no reason why E1 should be stronger here than here or here. E1 will have the same magnitude all the way around. It will also always have theta equals 0 with dA2. And so E1 cosine of 0, which is 1 anyway, gets to get pulled out of the integral, and I'm just left with integrating dA2. And if I integrate dA2 over my cylinder wall, what do I get? I get the surface area of the cylindrical wall. You're like, oof, what is that? Okay, so old memories from geometry. But the surface area is going to be 2 pi r, and we would have to give this a length L, which I haven't done. That's my fault. I should have stated that the length of my Gaussian cylinder is L. Like, wait, 2 pi r L, where did that come from? Okay, if you're not convinced, think of it this way. Take a toilet paper roll, cut it down the length, right, and flatten it out on the table.
Okay, you should get a rectangle, right? So if you take this thing and you think of it as a toilet paper roll just for the purposes of finding A2, cut it along its length, flatten it out, what do you get? You get a rectangle that has a length L, and then this side here is going to have to wrap back around into a circle of radius little r that's going to be 2 pi little r. Now we have a rectangle with side lengths 2 pi r and L, therefore the surface area is 2 pi r L. Okay. So my flux through my Gaussian cylinder is just the flux through the cylindrical wall, and is E1 times 2 pi r L. This is to be equated to Q enclosed over epsilon naught.
The question then is, how much charge do I enclose in my Gaussian cylinder? Well, the answer is 0. It's 0 because we said this is a conductor with sigma, which is charge per surface area, but the charge is on the outer surface, right? Property of conductors, by the way. Right? Conductors have charges free to move within them. So if you have a bunch of positive charges in a conductor, they're not all going to hang out in the center. They hate each other, right? They're going to get as far away as they can from each other. So in other words, they're going to move from the center to the outer surface. Well, guess what? My Gaussian cylinder does not enclose the outer surface. Therefore, it encloses none of the charge, and this is 0. By Gauss's law, if I equate this to this, I'm going to get E1 is equal to 0. All right, so by Gauss's law, E1 is 0. Okay, this is consistent with the property of a conductor, right? The electric field in a conductor, or in conducting material, let's say, in electrostatic equilibrium, is 0. Okay, for this reason. Right, the charge is going to move out, and therefore E inside your conductor is going to be 0. But Gauss's law, in case we didn't remember or didn't know that, will tell us that. Okay, it'll tell us, you know what, E1 is 0 because all of your charge moved out to the outer surface. And again, to apply Gauss's law, you have to believe in Gauss's law. The only thing that matters is the enclosed charge. And I know that for some, that's a hard thing to grasp, because it seems like these guys ought to matter. It's like, but there's charge on the outside. It's like, no, I get it. I get it. They do matter, right? They just don't matter in your calculation. But they matter in a way that you don't realize. They matter in the symmetry, right? The reason that E1 is radially outward in every direction in the horizontal plane is because of these charges on the outside, on the surface. Okay, so they do serve a purpose. They serve the purpose of providing you with the symmetry that you require to apply Gauss's law. It's simply that the accounting in Gauss's law couldn't care less about charge that is not enclosed by the imaginary Gaussian cylinder that you just put on the problem to carry out the calculation. Okay, so yes, weird, I know. Bear with me and bear with yourself. If you do this enough times, eventually it becomes almost automatic and it starts to make a lot more sense. But it does take some convincing at first. All right. So that is for region 1. Okay, now if you already know the answer, right, that E is 0 inside conducting material in electrostatic equilibrium, you don't have to do all this. You can just write E1 is equal to 0. But the goal today, of course, is to practice Gauss's law, so I wanted to do all the steps. Let's move on to region 2. Okay, region 2 is going to be outside of the cylinder, and we want to find the electric field there. Now, in that case, the electric field is not going to be 0, because we are going to enclose the charge that's on the surface of the cylinder. Okay. Now, I'm going to go a little bit faster here, but I'm going to explain why. Okay, now E2 looks exactly like E1. It's radially outward in all directions like this. And I'm not going to draw all of them because if it's the same thing as before, it turns out that this is going to be the same thing again. Flux will not change between region 1 and region 2. The only thing that will change is the amount of charge that you enclose. So let's not skip ahead too quickly. Let's set this up as if we maybe did not realize that yet. And we're going to draw a Gaussian cylinder that, there we go, is going to live outside of our actual cylinder because we want to find the electric field in region 2, and therefore our Gaussian cylinder has to live in region 2. So I'm going to draw my Gaussian cylinder. There we go. I'm going to make this a dotted line just for clarity. Cylinder is going to have a radius little r. This time little r is bigger than big R. That's why we wrote that. We're going to give it a length L before I forget. And we would draw the same thing. Yeah, we would draw dA1, dA3. Both of those are going to be perpendicular to E2. And then the only one that's going to matter is dA2. It's going to be everywhere along E2, and E2 is constant on the surface of the cylinder, and so on and so forth. And so the flux of E2 through my closed cylinder is simply going to be equal to E2 times 2 pi RL. Okay, you can go back and rewatch what I did and mirror it here and write everything out, and you will find no reason to write anything different. It's the same thing. It's the same math. Okay, a simple way to think of it is that flux doesn't know if you're in region 1 or in region 2. All it knows is that you're computing flux through a cylinder of radius little r and length L. That's all it knows. So it has no reason to give you a different output between each region. It is whatever it is. And what changes, though, is how much charge that you enclose. Right? Because now, yes, the charge moved to the outer surface of the cylinder, okay, but now I do enclose it. Now this charge that didn't used to be within my Gaussian cylinder is. And so this is going to be Q enclosed over epsilon naught. Well, what is Q enclosed? Okay. Well, Q enclosed is defined by sigma. Sigma is charge per area. Okay. So if I have charge per area, what I would need to do is multiply sigma by area to get charge. And so Q enclosed is going to be sigma times the surface area of the cylinder, 2 pi RL over epsilon naught. Now, there's something wrong with what I wrote. I purposely made an error that a lot of students make. These two things are probably not, should probably not be the same. Okay, so let's think about this. Your electric flux is calculated through your Gaussian cylinder. So this is correct because little r and L define your Gaussian cylinder. But here, I've overcounted my charge because I've overestimated my area. I should not multiply the area of this Gaussian cylinder by sigma. I should multiply the area of the actual cylinder that actually carries charge, right, this conducting rod, by sigma. And so I should not have 2 pi little RL. I should have 2 pi big RL. Be very careful with that. It's a very common error. Right? And so then by Gauss's law, I'm going to get E2 times 2 pi RL is equal to sigma 2 pi big RL over epsilon naught. 2 pi and L are going to go away. By the way, L should go away. If it's a truly infinite cylinder, L should not come into play. In other words, you could make your Gaussian cylinder as long or as short as you want. You should get the same thing. And then E2 is going to be sigma big R divided by little r epsilon naught. All right. So that's going to be my electric field outside of my Gaussian cylinder. Well, outside of my conducting cylinder. Duh. Okay. So hopefully, slowly but surely, we're starting to understand how you go about applying Gauss's law, right? You choose the surface that you place on the problem to solve the problem. It doesn't really exist, it's just a mathematical construct. But then you calculate the flux through the surface, you equate it to the charge enclosed over epsilon naught, and if you did it right, you get E. And sometimes it's a little harder than just the sphere that we did at first. Sometimes you have an object that has an inner region and an outer region. You just apply Gauss's law twice. Inner region to get the electric field inside, outer region to get the electric field outside. And it is not necessarily the case that E1 will always be 0. We're going to see a case right now with the same problem where it isn't. And just to be clear also, because this is a common one, once you have E1 and E2, a lot of students then ask me, well, I just add them, yeah? It's like, no. Each one is in for its own region. So it's really tempting because we do superposition a lot, and so we tend to be used to adding electric fields. But E1 is in region 1, there's none, there's nothing, okay, in this case. E2 is in region 2, okay. Now, that just tells you what the electric field is in each region. From there, if you want to study what happens outside of this conducting cylinder, well, you would use E2, because that's the electric field in that region. Whereas if you were to look inside, you would say, well, E1 is 0. That's the electric field in that region. So these don't add, they're just, each one is true in its region. That's it. Okay, so let me move this up. This was me planning ahead a little bit. And let's see why I drew that. Okay, now we have a different scenario. Assuming the cylinder is an insulator with a volume charge density rho, find the electric field inside and outside, basically. Okay, but now it's an insulator, it's not a conductor, and it has volume charge density rho. In other words, it has charge distributed throughout its volume. Okay, so in insulators, charge can exist throughout the volume of the insulator. Charge is kind of stuck like fruits in a fruitcake when it comes to an insulator, right? And so then we define rho, which is charge per volume. Okay. Now that is going to change our calculation of Q enclosed. But if rho is uniform, I still have cylindrical symmetry, right? So I'm still going to have E1 everywhere radiating outward. I'm going to have a Gaussian cylinder at first. Oh, come on. All right, so hold on. This is where, there we go.
Notability sometimes tries to test my my patience, but it is still a great writing app. So, all right, so there we go. We'll do the same thing as before, right? There's no reason why, for that matter, our approach should change, in other words, because we still have the right symmetry to apply Gauss's law. So, okay, let's go ahead and apply Gauss's law. Okay, this is going to be dA1, dA2, dA3, and now hopefully this is convincing. There's no reason why the electric flux should be any different, right? This is the electric flux through the closed cylinder is going to come out to be E1 times 2 pi RL. Okay?
That's what I'm saying. Once you get used to this, you can go very quickly because you know how to calculate flux through a cylinder or a sphere. Okay, well, there's no reason why it should be any different here than in the previous problem. However, Q enclosed, that is going to be a different story right there. All right, how much charge does my Gaussian cylinder enclose? Well, rho is charge per volume, so I need to multiply by this volume here in order to get all of the charge that is within my Gaussian cylinder. So it's going to be rho, and the volume of the cylinder is going to be area of base pi little r squared times height L divided by epsilon naught. Once again, just for clarity, this has a radius r and a length L. And so now, by Gauss's law, we're going to see that E1 is not zero. All right, by Gauss's law, I have E1 times, oh, come on, no. E1 2 pi RL is rho pi r squared L over epsilon naught. Again, L should go away if it's truly an infinite cylinder. Pi goes away, and if we simplify this, we get E1 is equal to rho, well, R simplifies actually, so rho R over 2 epsilon naught. All right. So that's E1 in region 1. It's no longer 0, but it has no reason to be because I do not have a conductor. I have an insulator. So now I have an electric field within region 1. Okay, region 2. Let's go ahead and do that. Okay, so region 2, I mean, look, I mean, at this point, hopefully you're really trying to catch on, starting to catch on, I mean, and, you know, realizing that it's always going to be the same thing. The difference, of course, now is that we want a Gaussian cylinder. You can't make this up. Thank you. All right. You want a Gaussian cylinder that is going to be bigger than your actual cylinder, right? Because you want to find the electric field outside. And so you're going to do this. Okay, this is going to be your Gaussian cylinder. It's going to have a length L, a radius R. Little r is going to be greater than big R. Okay. And then we have dA1, dA3, and dA2. Okay. Once again, the flux has no reason to change. It's the same symmetry. You're still computing flux through a cylinder of radius r and length L, so you're just going to get E2 times 2 pi RL. Q enclosed over epsilon naught is going to be different. You have to be careful here. Okay, rho is charge per volume. Right? So what I should do to find the charge that is contained within my Gaussian cylinder is multiply rho by the volume. However, not the volume of my Gaussian cylinder.
All of this is too much volume because guess what? Right here there's no charge, right here there's no charge. So the volume of the actual insulator that carries the charge. So this is going to be rho, but times pi big R squared L over epsilon naught. And by Gauss's law, these two quantities are equal to each other. So this is going to be E2 times 2 pi RL is equal to pi big R squared L over epsilon naught. And we find that E2 is equal to, well, my bad, I forgot a rho there, didn't I? Rho R squared over epsilon naught little r. Okay, that was, without rho, that definitely does not make sense in terms of units.
Okay, so that is E2. There we go. So, that is how you would apply Gauss's law in the case of the cylinder. Okay, which is an important case because it's pretty common to have to use cylinders, either for infinite lines of charge or infinite cylinders, sometimes infinite hollow cylinders, and then of course you can get creative. You could take an infinite hollow conducting cylinder and put an infinite line of charge in the center. What's the electric field everywhere? Those are very classic questions, okay? Because it turns out, of course, that if one were to just give you a cylinder with rho, well, this is it, like that's it. If you've done it already, it's very easy to find the answer. So that could be maybe an easy / medium test question, but it's likely not going to be the whole problem. Like it's just just too straightforward at this point. Okay, and the goal, since the goal is to find E2 anyway, let's say, well, okay, maybe you then want to use E2 to do other stuff. So it tends to be that these questions they're kind of the easy part of the problems that you get on exams. Like, okay, go ahead and apply Gauss's law, but we just want you to find the electric field because we want to ask you questions about that later. We want to continue the problem with that. Now and then you might get just a problem that's pure Gauss's law. It's a little bit harder. It's, charged objects nested within each other. But a lot of the time, you're just trying to get E so that you can then go find maybe the electric force or the electric potential difference. We'll talk about that next week, and so on and so forth. All right, so that's that for this problem. Speaking of charged objects nested within each other, let's do this problem. This is an extraordinarily classic problem, and my recommendation is that you spend some time on it and you convince yourself and you learn how to solve it, because if you don't know how to solve this, I would actually stay in bed on the day of the exam. I don't think it's worth getting up, because the odds of getting something like this, if not exactly this, in my estimate are pretty high. It's just such a classic problem, okay? And it's a great problem because it tests a lot of things, and it definitely separates those that just memorize Gauss's law and kind of hope for the best from those who truly understand what the heck is going on and how to apply it. Okay, so we have a charged insulating sphere, okay? Has a radius A, carries a total charge Q. This charge, because it's an insulator, is distributed throughout its volume. This insulating sphere is placed at the center of a spherical metallic shell, this thing, of radius B, inner radius, and outer radius C. The metallic shell itself carries 0 net charge. Okay, now that does not mean that it doesn't have positive and negative charges within it. It just means it has equal number of positive and negative, so net charge is 0. We want to find the surface charge density on the inner surface of the spherical shell and the surface charge density on the outer surface of the spherical shell. Eventually, we want to find the electric field everywhere. That's actually pure Gauss's law there. We'll get to that. Okay, so let's see.
How do we start this? Let's start by saying that Q shell is 0.
Okay, it's the net charge, but okay, still, Q shell is 0. Fair enough. The shell is a conductor, which means that, yes, it has equal amounts of positive and negative charges, but charge within the conducting shell is free to move. Now, if you don't put anything in the center, that's it. There's nothing to talk about. But if you do, the positive charge in the center is going to attract the negative charges contained within the metallic shell onto the inner surface. And all of a sudden, you will have a certain amount of charge on the inner surface. Let's call it Q inner. But with the same reasoning, the positive sphere in the center is going to repel the positive charges within the shell to the outer surface. And so now you're going to get Q outer. All right? So first things first, it is important to realize that this, in fact, happens. If you don't realize that this happens, you're going to get this wrong. Okay, so you get charge separation. Because the center is positive, negative charges move in, positive charges move out. Point is, you now get Q inner and Q outer. And the questions 1 and 2 say, oh, what's the surface charge density on the inner or the outer surface? But the truth is, okay, you might as well just ask me for Q outer or Q inner. It's the same thing, right? You're like, okay, well, I want you to tell me sigma inner. That's fine. Okay, sigma inner is charge per area. So it's the charge Q inner, which I'm going to have to find anyway, divided by the surface area of the inner surface of the spherical shell. That's going to be 4 pi b squared. Okay, surface area of a sphere is 4 pi r squared. The inner surface has a radius b. So, okay, that's sigma inner. And then if you want sigma outer, well, I'm just going to take Q outer and divide it by the surface area of the outer sphere, which is 4 pi c squared. Okay? All right, so that's really we're trying to get Q inner and Q outer. And typically in these types of problems, that's what you're trying to do, okay, in one form or the other. Now the question is, how do you go about that? Because there is a very systematic way of going about it. And it's important that you know that this is in fact a method in and of itself. So let me do the following. Let me redraw something that we can work with here. So this is going to be our outer shell. Okay, it's a conductor, so maybe let's use some gray, maybe to kind of make us think that it's some metal or something. And then we have this inner insulating sphere, and that's an insulator. Let's use a different color. Maybe we use light blue, like this. Okay, and this is going to have a charge plus Q distributed throughout its volume, and then we have some negative charge on the inner surface here, like we just argued. That's going to be Q inner. And then we're going to have some positive charge on the outer surface. That's going to be Q outer. Okay, Q inner and Q outer, cool. Okay, we want to find each one of those. We typically always start with Q inner. Okay? Now, how do we find Q inner? We're going to apply, now I call this Gauss's law in reverse. That's not an official name or anything, but at least I call it something so that we realize that it's a dedicated method, and I can then allude to it later. But Gauss's law in reverse is basically Gauss's law where instead of finding the electric field because you know Q enclosed, well, we go the other way. We're going to say we know that the electric field is 0, and therefore we find Q enclosed. Okay? So how do you do it? Well, you argue that your shell, your spherical shell, is a conductor, so that you know that everywhere inside the conducting shell, the electric field is 0. E is 0 in conducting material in electrostatic equilibrium. Okay. If that's true, and this is all spheres, yeah? So I draw
This is going to be a Gaussian sphere. I draw my Gaussian sphere of radius r such that the surface of my Gaussian sphere lives within the spherical shell. Then I will say that the flux through my Gaussian sphere has to be 0. Okay, but that's because E equals 0 in the shell. Okay, if there's no electric field in the shell, then there can be no field lines that poke through this surface in one direction or the other. There's just no electric field, so no flux. Okay? By Gauss's law, this implies that Q enclosed over epsilon naught is equal to 0, which of course means that Q enclosed has to be 0. Well, what is Q enclosed? Well, Q enclosed is how much charge lives within my Gaussian sphere. And the beauty of my Gaussian sphere is not only that it encloses the insulating sphere in the center, which carries a charge, capital Q, it also encloses the charge on the inner surface of the shell, which is Q inner. So Q plus Q inner has to be 0. In other words, Q inner has to be minus Q. And that's always true, by the way. However much charge you have in the center, it pulls onto the inner surface of the shell the exact opposite amount of charge. Okay, so Q is strong enough to pull onto the inner surface minus Q, but it can't pull on more, doesn't pull on less. Okay, it has to be exactly minus Q so that E is 0 inside the conducting shell. Okay, so we have found Q inner. Perfect. We therefore can figure out sigma inner. Sigma inner is easy. We already wrote it up there. Sigma inner is Q inner over 4 pi b squared, which is going to be minus Q divided by 4 pi b squared. All right, we found sigma inner. And again, you typically start by finding Q inner. What about Q outer? Can we find Q outer? Sure we can. To find Q outer, once you have Q inner, is actually easy. Now you could try to do the same trick with Gauss's law. It's just not going to work because you do not know what the electric field is outside here of the shell. It's not 0. Probably not anyway. In some cases it might be, but in general it's not true that it's 0. It's not a guarantee. It's only a guarantee inside conducting material. So instead, well, we can say the following. We can say that we know that the total charge on the shell, net charge, is 0. That was given by the problem. But where did Q inner and Q outer come from? They came from the shell, right? So it has to be true that Q inner plus Q outer is equal to Q shell. Just has to be the case. It's conservation of charge. All right, so by the way, that is how you find Q outer. You argue conservation of charge. And sure, it's nice that Q shell is 0 in this problem, but it actually doesn't have to be. Q shell could be anything. It doesn't matter. You find Q inner, Q shell is whatever they tell you, but then you find Q outer. All right, so Q outer is going to be equal to Q shell minus Q inner, which is 0 minus Q, which is Q. All right, so now we have Q outer, and we can have, or we can find, rather, sigma outer. All we have to do is divide Q outer by 4 pi c squared. So we're going to get Q over 4 pi c squared.
There we go. Super classic problem, super classic questions. Whether we ask for Q inner and Q outer or sigma inner, sigma outer, doesn't matter. You need to know how to find Q inner and Q outer. This is not negotiable. Like again, the chance that you find something like this or some version of it on the exam is pretty high. It's just a classic problem. All right, and then last question is find the electric field at a distance r from the center of the shell. In other words, find the electric field everywhere, which means that we're going to take our little arrangement here, and we are going to apply Gauss's law, but in each region. Okay, we're going to have to take it one region at a time. So let me get rid of this. Let's kind of fix this up real quick. We're going to have Q inner here, Q outer here. We know what they are, so that's nice. Okay, and so now it's pretty straightforward to apply Gauss's law. We just have to decide how many regions we have. Well, we have 1, 2, 3, 4. We have to apply Gauss's law 4 times. Okay, so I'm going to make 4 copies of this just so that we have them. And hold on, get rid of this. There we go. That's 1. And I think we have enough room to do them side by side, like that. And then we'll come down here and we'll finish down here. Okay. So everything's spherical. We have spherical symmetry. Therefore, in choosing between a Gaussian sphere and a Gaussian cylinder, I'm obviously going to choose a Gaussian sphere. That is the symmetry that makes sense here. I have to work from the inner region to the outer region. All right, so I got to go from region 1 to region 4, one region at a time. So I'm going to draw a Gaussian sphere here. That is going to be a sphere of radius little r. Now don't forget that this insulator, the spherical insulator, has radius a, and as we might expect, the electric field E1 is going to be radially outward, and let's just zoom in for clarity. This is going to be dA. dA is the outward normal. This is the same thing, same symmetry as the point charge that we did before, right? So I think if you understood the point charge part, this shouldn't be too bad. We can just convince ourselves rather easily that the flux through the closed Gaussian sphere of E1 is going to be E1 times the area of the sphere, 4 pi r squared, right? E1 is constant in magnitude and direction on my Gaussian sphere. Pull it out of the integral, integrate, multiply by the surface area of my Gaussian sphere. I get E1 is 4 pi r squared. What about Q enclosed over epsilon naught? All right, now that one's a little trickier, so I'm going to write 1 over epsilon naught so that I don't forget it. But then, well, how much charge is enclosed? Like, oh, damn. I have Q total enclosed in the insulating sphere, but I don't grab all of Q. I grab a fraction of Q inside my Gaussian sphere. So what I need to introduce is rho.
Rho is going to be charge Q divided by the volume of the actual insulating sphere.
4/3 pi a cubed. Okay, I need rho because rho is charge per volume. If I then take rho and I multiply by the volume,
which in this case is going to be the volume of my Gaussian sphere, then I'm going to get Q enclosed. So this is going to be, I guess I should write it like this. This is going to be rho multiplied by 4/3 pi r cubed. Okay, and so that's going to be Q over 4/3 pi a cubed multiplied by 4/3 pi r cubed, and don't forget epsilon naught down here, all right? And then 4/3 and pi go away, we get Q r cubed divided by epsilon naught a cubed. All right, and so by Gauss's law, E1 4 pi r squared is equal to Q r cubed over epsilon naught a cubed. All right, r squared kills the cube, and that's about it. We get E1 is equal to QR over 4 pi epsilon naught a cubed, radially outward. Okay, that's E1. That's actually the hardest one.
the rest is going to be pretty straightforward in comparison, because this one was hard because you had to introduce rho to get the right Q enclosed. But now if you move on to region 2 and you choose a Gaussian sphere that lives in region 2, like this, well, your flux, again, has no reason to be any different. Your flux does not know in which region it's being computed. It only knows that it's being computed through a sphere of radius r. So E2 4 pi r squared, that's just going to be your flux. What is Q enclosed over epsilon naught? Well, this time it's easy. You enclose all of Q from the insulating sphere, where you could grab all of it. So you can just say, well, if you set these two equal to each other by Gauss's law, you're going to get E2 4 pi r squared is equal to Q over epsilon naught, which means that E2 times 4 pi r squared, well, what am I doing? E2, rewriting it is not going to do me any good. E2 is Q, there we go, divided by 4 pi epsilon naught r squared. Okay, which, by the way, is Q over 4 pi r squared. That's the same as a point charge. But once you're in region 2, this thing here looks like a point charge. It's not a point charge, I get it, but it has the same symmetry. It has a certain amount of charge Q. So there's no reason why it should create an electric field any different than that of a point charge. So that's why you get E2 is Q over 4 pi epsilon naught r squared. Okay, moving on. This piece is easy. E3, I'm not even going to bother. We already know the answer because we used it in the first question. E3 is 0. E is 0 in conducting material in electrostatic equilibrium. That one's easy. Okay. And then finally, region 4. Region 4 isn't too bad. Yeah. Region 4, we're just going to have Gaussian sphere like this. And region 4, the flux, again, the flux does not know in which region it's being computed. So this is E4 dA. We're going to get E4 times 4 pi r squared. How much charge do I enclose? Okay, this is going to be Q enclosed over epsilon naught, where Q enclosed is equal to
Well, I have Q from the insulating sphere. Then I have Q inner, which is minus Q, and Q outer, which is Q, divided by epsilon naught. So that's going to be Q over epsilon naught. And therefore, same as in region 2, we find that E4, this is going to be Q over 4 pi epsilon naught r squared. Right. And so from the outside, this thing just looks like a big point charge with charge Q. All right. So hopefully that kind of clears things up when it comes to Gauss's law. I mean, we could spend a whole bunch of time on Gauss's law, but again, you cannot read about push-ups, you have to do them. It's the same thing with these problems. So my goal today was to do a few things. Let's just recap. Last week, we introduced electric fields, and we said, okay, here are the properties, electric force, electric fields, blah, 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 direction, electric field lines, all of that. Okay. And then at the end, we said, well, you know, it'd be nice to know a formula for electric fields for things that are not point charges, because not everything in life is a point charge. So we said, well, okay, well, how about slice and dice? Like, okay, that is a tool in the toolkit. This week, we moved to Gauss's law. This is another tool in the toolkit to compute the electric field E. Gauss's law, however, has restrictions. You have to have high symmetry. So you need infinite lines or infinite cylinders, infinite sheets, or something spherical like we just did. Okay, point charge or insulating sphere or whatever. If it's not one of those three, Gauss's law is not going to work. You have to use slice and dice. Okay. But the goal was to complement the first lecture and say now we have more tools in our toolkit to find the electric field. And then we had to kind of learn how to go about applying Gauss's law. Okay, realize that we're going to be choosing between spheres and cylinders, and really it's the symmetry of the electric field that dictates which one we choose. And then that Gauss's law is this weird thing because we put a mathematical surface on a problem. It's a disposable surface. We put it on there, we do a calculation, we throw it away, and then we say, oh, well, we got the electric field. And in addition to that, we only care about the charge that is enclosed, not the rest of the charge, right? So for example, here, or even in region 1, but in region 2, we only cared about Q. You might say, well, there was Q inner, there was Q outer. Should we not, like, does that not matter? And the answer is no, not in the accounting part of Gauss's law. It matters in the symmetry, right? Because we have those charges and because we have the symmetry, we get to apply Gauss's law. But the accounting of Gauss's law only cares about enclosed charge, as weird as that is. So my goal was to emphasize those things, to then do an example with a cylinder so that you know how to deal with cylinders, an example with spheres so that you know how to deal with spheres. And then from there, hopefully that's a good baseline to go do other problems that involve Gauss's law. But it is worth spending some time on because once you've done a few, it's actually not that hard to be good at Gauss's law. And that's quite, I mean, that's a good goal because, again, on exams, either we kind of give you a problem like this and we say, hey, oh, here we have these 4 regions, find the electric field in each region, it's just Gauss's law. And maybe it's more complicated, maybe we have to first find Q inner and Q outer, okay, it's still Gauss's law. And then there's another type of problem entirely where we give you a charge distribution and we're like, yeah, find the electric field, fine, but really we want to ask you about other things. So it's a requirement that you get the electric field if you want to solve the whole problem. Likely it involves Gauss's law, but really what we're trying to test you on is not necessarily just Gauss's law, it's also everything else that follows, you know, questions 2, 3, 4, and 5. You just have to not mess up question 1 to be able to get to questions 2, 3, 4, and 5. So anyway, that is going to be the end of the public portion of our physics review. As I said earlier, you can go to slackademia.com and you can sign up for free. The course is called Physics 8B Livestream, and if you sign up for that course, you will get all these live streams with all the practice problems that I solve, in addition to a bunch of homework problems that are solved as well if you want more practice. So it's a good resource to check out.
And then if you want a custom study guide, or if you want a study guide plus my help, then you can either enroll in an existing study guide on the website. If you cannot find a study guide for your class at your university or your college, contact us and send us your syllabus. We'll put it up on the website, and then you can decide if you want to subscribe or not. But that is what we do. We make study guides so that you don't have to. All right. Well, as always, thanks for watching. I appreciate it. This does not work if you don't watch me. And so, always a pleasure. And I hope you have a good weekend, and I will see you next week for electric potential. Be ready, because electric potential is a tough one, tough nut to crack, but it is doable. So we will do our best to explain why it really matters and what you really need to take away, at least to start building some confidence with electric potential. And then, of course, with practice, it gets